Okay, welcome to class today. We're going to be continuing with our work in Chapter 9 and specifically looking at inferences from two samples involving the mean, and we're going to look at an independent case and also a dependent or paired case today. So we'll be covering two sections. Sections 9.2 will be what we start off with, which is two means with an independent samples. And then we're going to move into 9.3, which are two dependent samples, and this will be what we can call matched pairs. Okay, so in the first section here, we're going to be looking at two independent samples and seeing how to conduct the hypothesis test and the confidence intervals for the difference between two population means. Okay, two samples are independent if the sample values from one population are not related or somehow naturally paired or matched with the sample values from the other population. So if you've got two samples that in no way are really related, then that would be an independent sample. If it's some kind of before and after type comparison, then that's going to be our matched pairs or our dependent. Okay, so dependent would be when you have matched pairs and they're matched up in some kind of inherent relationship. Okay, so looking at the independent sample case first, we're going to be conducting the hypothesis test and the confidence intervals for two independent population means. So some notation, very similar to what we looked at last class with the proportion type confidence intervals. Here we're going to be comparing two means. So we're going to have all this notation here with the sub ones, and then we're going to look at the same notation, but for population 2, it'll be subscripted with the 2s. So all these should be familiar to you except for the subscripting that we'll be working with today. Okay, so the requirements for independent samples, we're going to assume the values of our population standard deviation for both populations is unknown, and we don't assume that they're equal to each other. The two samples are independent. Both samples are simple random samples, and either the two samples are both large with their sample size being greater than 30, or both samples come from populations having normal distribution. So very similar requirements to what we would have done for just a regular hypothesis test and confidence interval involving means. Okay, this is our test statistic formula. I'm only showing you this just so you know what the calculator is doing. I am not expecting you to use this formula to calculate your test statistics. So just to be clear, in this section, just like in section 9.1, we are going to be getting all of our test statistics and all of our p-values from the calculator or StatCrunch. Okay, so this is what the test statistic would look like for this particular type hypothesis test. Okay, as far as the confidence interval estimate goes, again, we're going to get this from the calculator, and you can see this would be our margin of error formula if we were going to be calculating it that way. I'm mainly showing you this to show you what you're going to have in the middle of your interval, and that's the difference between the means, population means for the two populations that you're looking at. So you're going to put mu sub 1 minus mu sub 2 here in the middle, and you'll have a value here, and you'll have a value here that the calculator gives you. Okay, so I want to start by looking at this first example here. So what I would like for you to do, it says listed below are student course evaluations scores for courses taught by female professors and male professors. So we want to use a 0.05 significance level, so that's going to be my alpha, to test the claim. So here's my claim that the two samples are from populations with the same mean. Okay, so does there appear to be a difference in evaluation scores of courses taught by female professors and male professors? So the first thing I want you to do is to enter this in for L1 and enter this in for L2 in your calculator. And then we're going to go through and set this up. Once you've identified your claim statement and you've entered the data in your calculator, we're going to go ahead and set up our null and our alternative hypothesis. So with doing this, just like with the proportion ones, we're going to assume here for the null hypothesis that they're equal to each other, so that the mean from the first one is equal to the mean from the second one. When we look at our claim, it really doesn't indicate a direction like greater than or less than, so we're going to use does not equal for our alternative hypothesis. Okay. As far as our requirements go, we can kind of run through these quickly. The values of the two population standard deviations aren't known, and we don't assume that they're equal. The two samples are independent because they're not matched. The females and the male professors aren't matched in any way. The samples are small, so we do need to verify through our normal quantile plots that the two samples are from populations that are normally distributed, or at least close to being normally distributed. I'm not going to go through that because we've done a lot of normal quantile plots, but if you feel compelled and want to look at your normal quantile plot for that, you would see that they would be approximately normally distributed. Okay, and so here is our null and our alternative hypothesis that we already talked about. So as far as putting it in your calculator, what you're going to do is you're going to go to test, so stat test, and this time we're going to choose number 4, which is two sample, because we're comparing two samples, t-test. Okay, so because we're doing a mean and sigma is unknown, then we're going to use the t-test on this. So two sample t-test. This particular one, we had our data that was entered, so we're going to choose data. Make sure you've chosen L1 and L2, which is where we put our data. Choose your alternative hypothesis, so it was a does not equal. Choose no for pooled, and then calculate. Okay, when I do that, it brings this up. This is my test statistic, and this is my p-value. So I can use this to make my conclusions from. So my p-value here is large. So as far as my conclusion goes, my alpha is 0.05. So if I compare the p-value that I just found, which is this number here, to my alpha, which is this, then I see that my p-value is greater than my alpha. And when that happens, we conclude that we fail to reject the null hypothesis. Okay, as far as writing our non-technical conclusion, here's our setup of our null and our alternative hypothesis. Our claim was here. So, and we chose to fail to reject the null hypothesis. So we're basically going to have to hold on to this. So we're going to say there's not sufficient evidence to warrant rejection of our claim. Since our claim was the null hypothesis, there's not evidence to warrant rejection of the claim that female professors and male professors have the same mean course evaluation gender. Actually, since we fail to reject, since we are not going to reject our claim here, then we are going to basically believe that they do have the same mean course evaluation. If we go on to do a 95% confidence interval for the difference between these means, we'll go through the same requirements. As far as putting it in the calculator, we're going to go to stat test, and then instead of choosing the two sample t-test, we're going to choose the two sample t-interval. So this is going to be number 10 or 0, however you interpret that. So when we do that, we're going to go over here to the input screen, and we've got our data entered. We've got L1 and L2. We'll put in our confidence level and calculate, and this is what we're going to get. So here's our confidence interval, and remember, we're comparing the difference between the two population means. So I'm going to take this first endpoint, and that's going to go here. I'm going to put mu sub 1 minus mu sub 2 to represent the difference, and then I'm going to put my other endpoint over here when I write that interval. All right, so as far as interpreting our confidence interval, if we look at the interval here, it does contain 0. So if it does contain 0, basically what we're saying is that mu sub 1 minus mu sub 2 could equal 0, potentially, since 0 is between these endpoints. So potentially mu sub 1 could equal mu sub 2, and therefore the two means could be equal to each other. So because the limits contain 0, the confidence interval suggests that there is not a significant difference between the mean course evaluation score for female professors and the mean course evaluation score for male professors. So because the difference could be 0, then there is no significant difference. So I want to show you how to do this problem on StatCrunch. So I've already entered the data for the female professors and for the male professors. You can see one thing you may notice is that when we're talking about the independent samples that are being compared, you do not have to have the same number of data values in each data set in order to be able to do this. So we're going to use the female professors and male professors column. I'm going to go here to Stat, and I'm going to go to T-Test. This time I'm going to do to sample, and I'm going to do with data, and if you happen to have summary statistics provided, then you choose with summary. If I do with data, my first sample is the female professors, and the second sample is going to be the male professors. And when I go to set this one up, this was a two-tailed test. So for a two-tailed test, I'm going to choose the does not equal, and then I'm going to compute. And so here you see that my test statistic and my p-value are provided. That should match up with what we've already found. And so that's how you can find this from your StatCrunch. If I want to find the confidence interval, I'm going to go to Stat T-Test again to sample. This one again with data, and I'm just going to choose confidence interval here, and since it was a two-tailed test and my alpha was 0.05, then I'm going to do 0.95 and compute. Actually, I need to select these again, so I'm going to, okay, and then compute. And then here I have my lower limit and my upper limit that again should match with what we found using the calculator. Okay, here's one for you to try on your own. Okay, this one we've got a study of seat belt use involved children who were hospitalized after motor vehicle crashes for a group of 123 children. So this will be my N sub 1 who were wearing seat belts. The number of days in intensive care has a mean of 0.83. So this is going to be my X bar sub 1. And a standard deviation, this is going to be my S sub 1. For a group of 290 students, this will be my N sub 2. 290 children who were not wearing seatbelts, the number of days spent in ICUs has a mean of 1.39. So that's going to be my X bar sub 2. And a standard deviation of 3.06. So that's going to be my S sub 2. So we want to use a 0.05, so that's my alpha significance level to test the claim. So here's my claim that children wearing seat belts have a lower mean length of time in an ICU than the mean for children not wearing seat belts. Okay, so to set this one up, we're going to let population 1 be those that wear seat belts. So it's always good to kind of keep track of which one is representing the other. Population 2 is going to be that they don't wear their seat belts. Okay, so if our claim then, if we look back at the claim that children wearing seat belts have a lower mean length of time in an ICU than those that don't wear the seat belts. So we're basically saying that mu sub 1 is going to need to be less than mu sub 2. And so that's going to be our alternative hypothesis. We know that the equals is always in the null. So mu sub 1 equals mu sub 2 will be my null hypothesis. And then the less than is going to be the alternative hypothesis. When we go and choose our selections on the calculator, we're going to go to Test, to Sample T-Test. This time our data was not given, but we have our statistics provided, so we're going to choose Stats. And when we do that, it's going to prompt us for these things. So my X sub 1, if we look back, we're going to have, our X bar sub 1 would be 0.83. Our S sub 1 would be 1.77, and our N sub 1 would be 123. Okay, and then you can go through and enter the statistics for the second population. Choose the left tail, so the less than case, and then enter. And so here we see our test statistic. And we also see our p-value here. Okay, so our p-value and our test statistic, when you're summarizing this hypothesis test for me on a quiz or test, these are the things that I really need you to see written out. Even on these that we're doing entirely on our calculator, you have to show me your null and alternative hypothesis. You have to show me your test statistic, your p-value, your statistical conclusion, and then your non-technical conclusion. So at a minimum, this is what I have to see for you to get credit on a hypothesis test from Chapter 9. Okay, now Chapter 8, we worked with our test statistics and working out the calculations and the p-value, so I would expect to see that. In Chapter 9, we're getting everything from our calculator, so this is kind of the summary of what I would expect to see. Okay, so because our p-value is less than our alpha was, looking back, our alpha was 0.05, so this is less than 0.05, and so we would reject the null hypothesis. So this was our claim statement, and we're going to reject the null hypothesis in support of the claim. So we would say there is sufficient evidence to support the claim that children wearing seatbelts have a lower mean length of time in an ICU than do children not wearing seatbelts. So it's important, in Chapter 9, we see that we're comparing one sample to another. A lot of times that's important because if we were just comparing it to a number, that number may not mean anything. But to be able to compare it and say, yes, if you're wearing your seatbelt, children are not going to be in a series of, have a series of injuries, they're going to spend less time in ICU, then that becomes an important thing to know. Okay, so as far as the confidence interval on this one, if we go back, it says construct an appropriate confidence interval. This was a left-held test, and it had an alpha of 0.05. So if we're looking at an appropriate test, alpha is 0.05, so we would do 1 minus 2 times alpha for the left-held test. So that's 1 times 0.05. So that's going to give me 0.90. So I'm going to do a 90% confidence level, or 0.9. And I'll do 2 sample t interval for that. My data is already entered from the previous problem, and press calculate, and we're ready to get our confidence interval here. So this is my interval. Remember, we put mu sub 1 minus mu sub 2 in the middle here. As far as interpreting this, 0 is not in between these, and we can see that both values are negative. So it does look like the interval is shifted well below 0. So in order for that to happen, mu sub 1 minus mu sub 2, then it means mu sub 1 is going to have to be less than mu sub 2 in order for the difference to be negative, because both of these are well into the negatives here. Okay, moving on into this 9.3, looking at dependent samples or matched pairs. So we're going to basically be looking at doing some problems. This might involve something such as a before and after measurement, or maybe you're looking at IQ scores of husbands and their wives. So in some way they need to be matched together or paired together in order to use this technique. So a lot of times using the dependent samples with matched pairs is generally going to be better than using 2 independent samples. If you can match them, that's a good technique to use. All right, and so we'll look at the hypothesis testing and the confidence intervals for these. Okay, we have a lot of notation that's new here, so I want to take a minute and go over this. D is simply the difference between 2 values in a pair. So you just subtract the 2 values. Like if it's for a before and after situation, then you would do like the after minus the before and that type of thing to get the difference. The mu sub D, that's the population mean for the difference there. So the little sub D is referencing the difference. So it's the mean of the difference basically. D sub D bar, okay, is going to be the mean of the differences. So anytime we have this line across it, it's the mean. So the mean of the differences for the paired data. S is standard deviation. So S sub D is going to be the standard deviation for the differences for the paired sample data. N is going to be the number of pairs that you have in your sample. Okay, so as far as the requirements, the data is going to be dependent and it's going to be matched pairs. It still needs to be a simple random sample, and either the number of pairs is large, which means n greater than 30, or they have differences that are from a population with a distribution that's approximately normal. So we're going to really, in this section, focus on their differences. Okay, here is our test statistic. If you notice, this test statistic is actually very similar to the one that we've used before, x bar minus mu divided by s over the square root of n. It's just everything is in relation to the difference, and that's really the only thing we see that is different. Okay, so our procedure here, we're going to verify that they are matched pairs and the requirements are met. We're going to find the difference between each pair of sample values. We're going to find the mean of the difference and the standard deviation, and then we're going to use just a regular t-test. So we're not doing, it's not going to be the two sample t-test, it's just going to be your regular t-test, because we're going to take and look at only the difference between the two. All right, so first thing I want you to do is to put this in for L1 and this in for L2. And then for L3, you're going to do L1 minus L2. Okay, so entering the data here, the data lists the ages of actresses when they won Oscars in the category of Best Actress, along with the ages of actors when they won Oscars in the category of Best Actor. The ages are matched according to the year that the award was presented. There's a small random selection of the available data, so we want to use a sample data with an alpha of 0.05 significance level to test the claim. Here's our claim that for the population of ages of best actresses and best actors, the difference have a mean that's less than 0. Okay, so this is just kind of showing you your calculator screen. You've got put your L1 and L2. L3, you want to go make sure you've gone all the way up to the top before you type in L1 minus L2, and that's going to fill in these data values for you here. As far as the requirements, we need to make sure that they're paired, they're randomly selected, and the number of pairs in this case is not large, so we would need to look to make sure it's is normally distributed. And if you look at the normal quantile plot for the differences, you would so for L3, you would be able to see that it does in fact have approximately a straight line pattern with that. Okay, so as far as setting this up for our null and alternative hypothesis, we're going to just say that the mean difference is 0 for our alternative, for our null hypothesis. If you remember, that is equal to, and then our alternative hypothesis, the mean difference is less than 0, and that would be our claim. Going back to our claim statement here, the claim is that the differences have a mean less than 0. So we're going to use just our regular t-distribution. So what we're going to do is we're going to go to our test menu, except this time instead of doing two samples, we're just going to do a basic t-test, and this t-test is going to be of the differences. So we're going to be only using L3. We're not going to use L1 and L2 anymore. We're just going to use L3. So you're going to go t-test. This one we had our data entered, and our data was in L3. You want to be sure you put your null hypothesis value there, which was 0, and our alternative was the less than, so you choose that. Okay, and press enter. So this is going to be my test statistic, and this is going to be my p-value. So this p-value is going to be greater than the alpha, and therefore because it's greater than the alpha, we're going to fail to reject the null hypothesis. And as far as writing our interpretation statement here, this was our original claim, and we said that we are going to fail to reject the null hypothesis. So we're going to say there is not evidence to support the claim. There's not evidence to support the claim that for the population of ages of best actresses and best actors, the differences have a mean less than 0. Okay, so we want to do a confidence interval for this one. If we set this up, we're going to use a 90% confidence interval difference. So we're going to, again, we're not going to be using the 2-sample test. We're just going to be using a regular t-interval, except we're going to make sure that we're doing this for L3, which is their difference. Okay, so we're going to do regular t-interval, but for L3, choose a 90% confidence interval, and then here we have our answer. So the interval is somewhere between negative 24.2 and 3.8 years. So as far as interpreting this, we have a 90% confidence that the limits of negative 24.2 years and 3.8 years contain the true value of the mean of the age differences. So basically, the confidence interval includes the value of 0, so it's possible that the mean of the difference is equal to 0. If that were true, then we would be basically saying there is no significant difference between the ages of the best actresses and best actors. So back over here on StatCrunch again, I wanted to look at this example and show you how to do one that's paired data using StatCrunch. So we'll go to Stat, and we're going to go to T-Test, and we're going to do, in this case, StatCrunch does give us the option of this paired, so we don't have to go through and find the difference like we do on the calculator. So we're going to do paired. We'll enter actresses for sample 1, and for sample 2 we're going to do the actors. In this particular one, we were saying this would be a less than, and so then we're going to calculate, and so we'll see from this our test statistic is the same as we found on the calculator, negative 1.55, and our p-value is 0.0973. As far as the confidence intervals go, if we look at going to Stat, T-Stats, paired, here we'll choose confidence interval. And on this one, we're going to do a 90% because 0.05, since it's a left-held test, we need to double that. So that's going to be 0.90. And compute. And again, I forgot to put in my samples. So I've got actress 1 in sample 1, actor in sample 2, and compute. And so here I see my lower limit, which is negative 24.17, and my upper limit is 3.77, which is exactly what we got on the calculator. So I don't have a preference whether you use the calculator or StatCrunch, as long as you can find it using one of those. So even though it's the dependent paired case is a little bit different than the other two population samples, it is something that's very important to understand because it's used a lot in looking at before and after situations and so forth. So here's one for you to try on your own. This one is paired. It's looking at the body temperatures at 8 a.m. and at 12 a.m. So try finding a 0.05 significance level to test the claim that there's no difference between body temperatures measured at 8 a.m. and at 12 a.m. Okay, so this is what you should have set up. Okay, so here we have the mean of the difference would be 0 because on this type it's always going to be equal to 0. And the mean of the difference is not equal to 0 as our alternative because there's no direction specified. So it turns out in this one that this is going to be our claim statement because it's saying that there is no difference, and that would indicate that would be corresponding with our null hypothesis. So our test statistic, we're going to get that by going to, once we've done our L1 or L2 and our differences, then we'll go to test, t-test. Our data has been entered, so we'll do data. Our mu sub 0 is 0. And we're going to do L3 for our list because that's where our differences are, and a tail that does not equal, so it's a two-tailed test. That gives us our test statistic and our p-value. So our p-value is very small since we've got this e-4 over here. That's 0.000291. That's definitely less than our alpha, and so we would reject the null hypothesis. So since our claim is in the null hypothesis here, we're going to talk about whether or not we can warrant rejection of the claim. And since we reject our null hypothesis, we're essentially rejecting our claim. So we would say there is evidence to warrant rejection of the claim. And one thing I've always had people that wanted to think that warranting to have a that didn't understand what warrant means, and basically it just means to justify. So there is sufficient evidence to justify rejection of the claim, or to allow us to reject the claim. So, and the claim being that there is no difference. So if we're rejecting the claim that there is no difference, then basically we're saying that there is a difference between those two. So here, if we construct our confidence interval for this, then we're going to do another t-interval again for L3. And so on this one, we're doing the 0.05 significance level. So that means we would do 0.95 for our confidence interval, since it's a two-tailed test. And that gives me this. Confidence interval consists of negative numbers only and does not contain 0. So because it doesn't contain 0, then we are saying that there is a difference between those. Okay, that finishes up what I would like to cover in Chapter 9. Remember, in Chapter 9, we are comparing two different populations for all of these, but in each case, we are getting our test statistic and our p-value only from the calculator. So do not try to be doing these calculations by hand. It's not something that we've got enough time to spend to go through all of that. So we're just looking at how to do these on the calculator and StatCrunch. So again, just focus on that part. You still need to show me your null and alternative hypothesis, your test statistic, your p-value, and your two conclusions. But you do not have to show me a lot of calculations for these. Okay, if you have any questions, let me know. I hope you have a good day.